Okay, everybody can see the presentation? Sweet. Good to see you all. It's been a while. I'm Advite. If I haven't met you, I'm pretty sure I indirectly or directly know everybody here. So good to see you all. I have been thinking a lot about LLMs and agents, and I've just been blown away by how rapidly everything has been changing. And I really get the sense that we're in the middle of like a huge transition, and nobody really knows fully what all of the best practices are, let alone like what it's all going to amount to. But I think we're all sort of starting to see some really exciting use cases, including a lot of like, I don't know, software engineering automation, like automatically generating code, automatically classifying things. And I'm also starting to see like a wide distribution of like sophistication of these systems. And my sort of excitement here is that I think we're on the cusp of building these things called auto-optimizing agentic systems, for lack of a buzzword maybe. But it's really like LLM-based systems that are able to accomplish more and more sophisticated tasks. And as they go about accomplishing these tasks, they sort of synthesize learnings in order to make incremental, or so in order to make the next batch of agent runs more effective, essentially. So I think this is not just possible. I think people are actually doing it in practice. And I think if we're actually able to accomplish this, it seems like a general purpose structure that can be useful in many contexts, not just a business context. And so what I'm here to talk about today is like some of the underlying principles around how a self-learning system can come to be, might come to be. And there may be a collection of ideas that are all complementary that I think when applied together result in something really interesting. So with that, let's jump in. First, I want to talk about the motivation here. I mean, I already talked a little bit about what this might amount to, but in the context of a business, I think you can think of knowledge workers as primarily researchers, right? We're all knowledge workers. Concrete examples of this would be like, as an engineer, I had to implement sound effects for the GoGuardian Hall Pass product last week. And I don't know anything about web audio or the frameworks or FFmpeg or how to generate actual FFmpeg like output, whatever. And so I spent the vast majority of my time using LLM-based tools to learn about these technologies, and then also learn about a bunch of internal stuff, right? So we have a specific feature that we're trying to build. It's being built in the context of real customers that have real challenges that we're hoping to solve. And so understanding their mindset, their day-to-day, and then sort of stitching that together with the sort of technical understanding of how to implement stuff is basically the role of an engineer, I would say. But it goes obviously beyond engineering. I think if you think about support, it's sort of very clear how that's a research-oriented role as well, right? We need to understand not just how the products work, but also, again, the customer and the specific problems they're having, maybe juxtaposed to dozens of prior instances where this stuff has happened in the past. And I guess if you squint, this is basically literally every role, right? So salesperson is going to be primarily research-oriented, marketing, again, research-oriented. And so my view here is that we're all researchers, and that the latency and the quality of the research that we do is the primary bottleneck for the output of the entire organization. So latency meaning how quickly can we go from question to answer, and then quality, of course, being how accurate or valuable is that answer or insight. And so in the pre-LLM world, the way that we went about doing research is with obviously search engines or whatever, right? But I think perhaps more perniciously, the way that we resort to doing research in a company is actually like talking to each other in the form of Slack messages, in the form of synchronous meetings, and those messages and meetings result in interruptions. And we all know the sort of compounding effect of interruptions as it relates to like our own output. And if you scale that out across the whole organization, it's clear to me that like we're sort of constantly interrupting each other and constantly stuck on finding answers to questions. And so if we can solve this problem, or at least make it incrementally more efficient, I think the net gains will just be incredibly exciting. And so this is like the main motivation in my mind. How do we improve the latency of going from question to answer? And then how do we improve the quality of the actual answers? As we all know, LLM output quality varies widely. So you see some examples that are trending on Twitter of people sort of like one-shotting apps. It seems like that's extremely rare in practice in terms of how likely it actually happens. And as Brian was talking about in the Lunch and Learn a few weeks ago, there's this whole sort of new arcane art of prompt engineering where people are experimenting with certain words or sentences or structures, and we're scratching our head asking like, why does it work better with this structure as opposed to this other structure? It really feels like an art. But despite it being an art, there's clear examples of LLMs being extremely effective in certain circumstances. And so my question is like, how do we systematically and reliably get our LLM systems to be that effective? And this is also another interesting thing, which is, again, coming back to the whole organization as a big like knowledge worker, researcher ecosystem. If we're able to reduce the latency of questions, it's actually interesting. You can ask more questions. So in a engineering research context, this might be less obvious because there's like a concrete end after which you have enough information to be able to do what you need to do. But in like a more general business context, let's say it's like understanding your customers. If you can ask one question, get an immediate answer, that tees you up to ask the next question and the next question and the next question. And my view is that the more questions that we can ask, the more nuance of an understanding we can develop of our customer base and their problems, and again, be really, really more effective. So the framing here is, how do we improve the effectiveness of LLM-based systems to sort of unlock that rare, let's say, top 5 percentile of effectiveness? And then how do we do that return the answers quickly so that we can ask more questions? Okay, so with this framing, I think that there's a few sort of principles that we can use in order to get us there. And so the first principle is evals. So eval being short for evaluation. So we have dozens of LLM systems here internally within the company already. And my understanding is that very few, if not, I'm not even sure if a single one has like a quantitative evaluation like framework, test harness, let's say, right? And this is basically expressing the desired behavior of the LLM system in the form of input-output pairs. So if I have some input, let's say it's a deck that I want to generate in the context of Pear Deck, the output might be an expectation of what the LLM system should produce, right? And in the process, we can collect dozens or hundreds of such examples. And once we have these examples, we can use the examples to judge the performance of any LLM system, right? And I think this is an important idea because it takes prompt engineering from this like arcane art thing to instead a little bit more of a systematic thing, where sure, we might not know why certain prompts perform better than others, but we can objectively stack rank certain prompts over others in order to maximize some eval score, which ideally captures the essence of the desired performance of the system, right? So I guess it's just this desire to want to move from qualitative, vibe codey, hand wavy, this feels good of a system to no, let's actually quantify or articulately describe what good means in the quality of the answer, the format of the answer, the lack of, I don't know, offensive language in the answer, whatever, right? You can imagine these dimensions or rubrics that we can use. And then once we have this mechanism to score outputs, our job here is to then simply iterate on the prompts in order to maximize the outputs. And so here, the idea is quantifying LLM performance on real-world queries gives us a single metric that we can optimize. And so instead of having to constantly try something, qualitatively judge the output, make an adjustment, we can instead underpin this whole iterative process with this metric and then optimize. And so this leads me to, let's actually talk about the structure of an eval. So breaking it down, we have the user input, and we pass the user input through some LLM system, and the LLM system produces some LLM output. And here, this is arbitrary, right? This can be a paired deck, this can be a block of code that actually needs to compile. It can be some output that we need to send to a customer. It can be some research report, any LLM output, either like direct output or translated output, meaning the output was turned into something else like a deck, right? So given the user input, the LLM system produces the output. What we do is we juxtapose that with a desired output. And this is usually initially human authored. And then what we do is we compare the LLM output versus the desired output, and then we turn that into a quantitative eval. And so how this is done is actually interesting. And obviously, the more accurate your mechanism of comparing LLM output to desired output and quantifying how similar they are, like the more accurate that is, I guess the more effective you can be in actually optimizing this LLM system to do whatever it is you want it to do. So this is the structure of an eval. The interesting idea here is that once we have this eval structure and many of these input-output pairs, what we do is we simply iterate on the prompts in order to maximize the eval. And in a way, we're really agnostic to the prompts. Like, we don't actually care what the prompt is. It's just a matter of whether it's actually quantifiably improving the thing that we care about. And so if you squint, actually, this looks exactly like training ML models. So take something like the Beacon classification model, where instead of an LLM system here, you have a neural network, and the user input is actually a page content, right? And the LLM output is a classification of the categories of that page content. In the context of Beacon or Smart Alerts or any situation where we've trained a neural network, we've just collected hundreds, if not thousands or tens of thousands of these input-output pairs. We have a mechanism to quantify the model output versus the desired output in the form of a loss function, and that produces a single metric loss. And what we do is we simply iterate on the neural network weights in order to maximize the loss or minimize the loss, whatever I think you get what I'm trying to say, right? So it's literally the same thing in LLM world, where instead of updating the neural network weights, we're simply updating the prompts. And the objective is just to simply maximize the eval. So I find this way of looking at LLM-based systems to be very, very interesting. Again, it transitions from this artistic thing to this really systematic thing. And I think that there's real power in this way of thinking about it. Because again, the more specific you can be at articulating what your desired output is and quantifying the eval accurately, I think you'll get the prompts to naturally converge towards whatever it is you're trying to do. Okay, so that really begs the question: how do we iterate on the prompts? There's obviously, again, hand-wavy ways to do this, meaning run the LLM system across the canned input and desired output, producing an eval, look at some of the outputs as a human, and then make some change to the prompt, and then run it again and see if it improves the score. And I'm sure you could do this and be pretty effective. But it turns out that we can actually use LLMs themselves to iterate on the prompts. And moreover, we can be super systematic about how we go about iterating on the prompts, meaning instead of just trying a bunch of changes willy-nilly, you can use a statistical mindset and this technique called Bayesian optimization, which we won't get into, in order to be really systematic about, I want to try this specific iteration, or I want to continue to explore this branch, this sort of set of prompts that are all common, because this commonality might be compelling, right? You can kind of think about that in a statistical lens and use that to sort of really optimally iterate on the prompts. And so it turns out that this is a really compelling idea to the point where it's been now codified into a framework, and the framework is called dspy. It's not. I don't think it's dspy. It's like dspy. I don't know what the DS stands for. I'm pretty sure it's not even like data science. But anyways, it's called dspy, and what it is it's a Python framework for training LLM systems with input-output pair training data. And again, instead of producing neural network weights like we were doing with PyTorch, dspy instead produces LLM prompts, which then obviously can be consumed via inference to produce novel outputs for novel inputs, which is the whole point of what we're trying to do here. So how does dspy work? It's actually very simple. First, you create this thing called a signature, and the signature basically describes the interface of your whole LLM system. And so you have here a question in the form of a string noted as an input field, and then you also have a response, again, which is a string noted as an output field, and then some rough high-level instructions here. So I wanted to experiment with this, and I wanted to, again, in the context of improving the efficacy of our knowledge workers or expediting research, a huge knowledge base we have internally is Confluence. And so I wanted to use dspy to essentially build an agent system to be able to search through Confluence in order to answer like business questions. And so you're an assistant for GoGuardian employees that has access to internal Confluence knowledge base, provide a concise markdown formatted answer to the user's question using quotes from the page content with links referring back to the page, right? So simple prompt. And here I provide dspy these two tools. So a tool is in like the LLM world, a mechanism for the LLM to make a function call that can be processed out of band, such that the results of the function call get piped back into the LLM thread, so the LLM can then continue. So here we have two tools. The first is run CQL. So Atlassian, for some reason, has like a full query language for Confluence called CQL. That's sort of SQL-like, that allows you to query specific fields and stuff like that. And it turns out LLMs know a lot about CQL and its syntax and the fields and so on. And so here I just wrote a wrapper around the Confluence API that allows an LLM to just simply produce some CQL, and then behind the scenes I'll run it against the API, get the results, transform the results back in markdown format, and then pipe the results back into the LLM thread. And so literally all that is just a single Python function, ordinary Python function, that takes in the CQL string and returns the markdown text, right? So it's dead simple. And I'm just wrapping it in this dspy tool thing that gives it a description, meaning like what happens when you call this tool. And then same thing for the second tool. It's called getPage, and it's takes in as input some integer page ID, gets the page via the API, transforms that page into markdown format, and that's it. That's all this function getPage does, and I'm wrapping it in this dspy tool thing. And then I have this agent, which is dspy.react, is this like agent thing inside of dspy. And I give it the agent signature, which is this thing, and then I give it the tools that it's allowed, and that's it, pretty much. And using this, I can basically collect a bunch of input-output pairs. So here's an example that I came up with. How can an admin set up a school in Hall Pass? And the answer, based on some MVP doc we have in the Confluence knowledge base, is an admin can set up a school, refer to a site from within product settings, blah, 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 blah. This is basically how I want my LLM system to output stuff. And I hand wrote dozens of these things. And then basically, without getting into more code, there's a very straightforward mechanism to take the input-output pairs and take the sort of signature and tool structure and optimize the prompts, basically. Meaning, like, you can imagine a prompt. Actually, I'll just show you what the resulting optimized prompt was. And so this is, as an assistant for GoGuardian employees with access to the internal Confluence knowledge base, your task is to provide detailed markdown formatted answers to the user's questions about the Hall Pass feature. using the CQL, blah, 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 blah. And this is fully generated, right? And not only is it fully generated, but this specific structure, its performance on the training data set is sort of mathematically optimal, I guess you could say, compared to hypothetical other prompts, which could have plausibly worked, right? And one interesting thought here is that you can see that the prompt is specifically about the hall pass feature, which actually is an accident in the form of I was hoping to build a more like general purpose Confluence thing that knows about all of the products. But just because I happen to be working on hall pass right now, I have more questions in my training data set about hall pass than other products. And so you can see that the prompt almost like overfit onto hall pass itself, which really suggests that if we instead had a more representative data set about the real questions that people would hypothetically ask with this tool, and as well as paired obviously with correct answers, that this result would in turn more accurately reflect the sort of examples that we're actually providing. And so behind the scenes, dspy also integrates with MLflow, which is a great library or like a suite of things really that allows you to track ML model training runs in the sort of software 2.0 world, meaning training neural nets and things like that. But it also has an integration for this like software 3.0 thing, which is actually like tracing agent runs. And so here you can see a novel question comes in: how does GoGuardian's beacon suicide and self-harm detection work? And here on the left, you can see the actual trace. So it makes some, I think the blue things over here are actual like LLM calls. And then the underscore call maybe is like some tool run. I don't know exactly, but you can kind of get a sense of what it's doing here. First, it just does a general call, and then it calls the run CQL tool. And then afterwards, it does another general call, and then it does a get page of some underlying page, and then it does another call, and then another call, and then it produces this final output. And so you could see some of the reasoning behind the scenes here, and then you can see the actual response that it produced, which looks pretty reasonable to me. And so all of this, like the actual plumbing of performing the tool calls, parsing the LLM output, even doing this tracing, all of this comes for free as a consequence of literally like these 2 pages worth of code, right? So I find this again to be super, super interesting because it kicks us up one notch higher level where we're framing what our objective is. We're collecting like real examples of how we want the performance of the system to be. And then to the extent that it's necessary, implementing actual tools, which are actual simple Python functions that are able to call APIs or produce decks or whatever. And by putting it through this optimization process, we get this, as well as the ability to run inference like this. So I think of this as super interesting again, much more simple in my mind, honestly, than like a lot of like the LLM frameworks coming out there, like LangChain and things like that. And frankly, much more systematic in terms of articulating what it is we're trying to accomplish. Okay, so here's the next idea. We've talked about evals, we talked about dspy as a framework to automatically optimize LLM prompts. And again, I'm less attached to the framework specifically and more interested in this notion of automatically revising prompts so as to maximize some eval. I think that's the key idea. And so I think if you have that, you get to self-improvement really. And this is where it gets really interesting. So as you start with the V1 of your LLM system and you deploy it in the wild and people start to interact with it, you'll get examples of real questions that people pass through the system. And you can see what the actual performance is with tracing or with logging or however you want to visualize it. And you can then say, hey, this example was actually really good, meaning it's a good question and it was a good answer. So what I'm going to do is I'm going to memorialize it as a part of the training data. Or alternatively, the inverse, where this outcome was really bad. I wish it had instead made so-and-so searches in order to produce this final result. And you include that as a part of the training data. And as you do that, the training data set grows and grows and grows. And that dspy is then able to reliably take advantage of the new information that you're essentially providing it in the form of new training data examples and further refine the prompts in order to get an even more effective LLM system as defined by your eval. So there's a feedback loop here. The more usage you get, the more training data you have, the more accurate your LLM system becomes, and presumably that leads to more usage. It's not too dissimilar. In fact, it's literally identical, I think, to the feedback loops that we have in training neural networks and exposing them to user-facing queries. So I think just the sheer similarity is fascinating to me, because we've seen already maybe like a half decade or a decade of companies and businesses being built where the premise is this sort of feedback loop where they were training neural networks. And so I think now in this new era, if we apply those same principles, we get the same feedback loop. It stands to reason that that'll translate to the same kind of effective products or ever increasing effectiveness over time, which is really the key. And moreover, where software 2.0 models were sort of limited in their domains, I think software 3.0 agents are not limited at all, meaning you can take in text input, you can take it audio input, image input, whatever, and you can produce any output, particularly to the extent that it can be intermediate sort of like JSON output, which you can then further translate into some other downstream artifact. And so in a way, these LLM-based agent systems are much more extensible, dynamic, useful in more contexts. And I believe that we can use the same sort of feedback loop structures that we had in the software 2.0 world in this software 3.0 world. And I think it's super cool. Okay, so beyond prompt improvement. So if you, like, again, coming back to knowledge workers, I thought a lot about how do knowledge workers, like how do all of our employees get our work, how do we get our work done over the course of the day and the week? And you basically interface with maybe a half a dozen or so internal systems, including the code base, including maybe Confluence. Slack is a huge one. Email is big too. Salesforce. I forget what tool we use to host our support tickets. Maybe it's Zendesk, maybe it's something else, but you get the idea, right? These tools basically contain all of the raw knowledge. We even have actually sales call transcripts, right? And so like all of that raw data exists, and we're asking business questions that could be answered by all of that raw information, like pretty reliably. Almost like if you look at most Slack channels and just simply look at the questions people are asking, I would wager maybe 80% of them are easily answerable by simply like looking it up in the form of, and I guess the reason I'm struggling is like, it's kind of hard to look it up. Like you don't know exactly where that information is. Like, is it in the code literally, meaning like the PRD is stale, but we've sort of iterated on the code base and the feature now has changed? Or is it sort of in the minds of a support person who answered this similar ticket like last month? We don't know where that information actually lives, but maybe it lives somewhere. And so the sort of claim or suggestion here is that I think we need to really think about where our business knowledge lives and really start to enable LLM-based agent systems to have reliable access to this business knowledge. So I think it's like a structuring problem, meaning let's have a strong point of view around where the information lives, how it's stored, and so on. And then it's like an access or prompts or agents problem. around how do you unleash these LLM agents to have access to it. And here we've already talked about how to do that quantitatively speaking. So I think we need to do this, and the net result is going to me, very clearly be more effectiveness to knowledge workers on the latency and quality domain. But also beyond this, I think in addition to reads, agents really need to be able to write knowledge back into our knowledge systems. This I think is extremely untapped. Many of us on this call use Cursor to write code, and you may have had this experience where Cursor sort of figures something out about your code architecture, and that specific chat thread happens to be just like really good. It's like really effective at implementing feature X. But then you start with a new chat session, there's no longer that context, and you ask it to implement some feature, and it's really, really bad, right? And so to me, what's happening behind the scenes is there's some insight that the model was able to come across in the process of its sort of like agentic exploration that enabled it to be effective at a set of tasks. And we need to enable some mechanism to take that insight and repackage it back into the knowledge base, whether it's the code base, whether it's Confluence or something like that. And I think this is a generalizable idea beyond just code, right? So take something like an exploration call that we do with a prospective customer, right? There's so much information in that call about who the customer is, who the specific people are that we're speaking with, what their circumstances are, what they're trying to accomplish, whether they've tried other of our competitors' products, whether they have funding constraints, a million questions, right? And necessarily today, for the most part, I would say that information just sort of lives in the minds of the people on the call and is sort of stuck there. And the only way to get access to it is to talk to those people firsthand. And very rarely does that knowledge make its way back into something that's like concretized. And so I think we need to figure this out, because that knowledge more or less is just being dropped on the floor. And almost in the worst, like tragic case, like that knowledge might actually exist in the minds of some people within the company, but some other group in the company might be asking a question that could be answered by that knowledge. But because it's sort of a silo, so to speak, these two people never even talk or have the opportunity to know that they should be having a conversation. And then that team over here just simply ends up making a suboptimal decision. In my mind, that's actually the more common scenario, where as the company gets bigger and the teams get more and more isolated, we simply don't have a reliable mechanism to learn from each other in this sort of cross-organizational way. And this is where I think the opportunity is. I think as these LLM agent runs happen, and whether it's sort of processing raw customer interactions or going through the code base or whatever, right? We need some mechanism to take conclusions that the agent run had, pipe them back into the knowledge base so that the overall LLM system becomes more effective. And again, tying this back to evals, you can literally quantify the performance of your whole system, including the knowledge base itself, meaning as these write-backs are happening, you can then literally just have a test suite of canned questions that are run, and using the eval mechanism that I described earlier, quantify the performance of this new version of the LLM system with a new knowledge. And every night, maybe you can just take like a snapshot of this is what the performance is today. And you could just continue to do this every day. And as the eval base expands, and the knowledge base, meaning like the write-backs improve or increase, you can reliably know that the aggregate system is actually improving in its efficacy. And so I think we got to build this. And it seems so clear to me that as a consequence of building it, like all of our jobs across the entire company will become more effective. And perhaps even more excitingly, that we can apply these principles in probably every domain, any domain out there, meaning you can probably apply these principles to educating kids. You could probably apply these principles to generating educational content, whatever it is you want to do. And maybe the most exciting part is that these ideas are super interesting. They're compelling. Some people have tried them, and they've resulted in actual positive outcomes. but they're not even close to what you might call the best practices or the standard approach to the problem. And that's because there is no standard approach to the problem. It's kind of uncharted. And it's in this unchartedness that I think is the opportunity, because if you figure out how to do it, you're necessarily going to be ahead of everybody else. And you'll be ahead in the form of being drastically more effective as a knowledge worker organization, which, man, that seems really, really good if you can do that. So here I am, like, super excited about this. I've like dabbled with these tools. I have some points of view around how we might think about an internal knowledge base. Maybe some pragmatic principles around we probably shouldn't discard all of the knowledge we already have in our systems and figure out a way to utilize it, as opposed to maybe like a blank slate system. But the reason that I wanted to sort of give this talk today is to start a broader conversation with everybody here, see if these ideas resonate, and see if we can articulate like a vision for where we want to go on building something like this within the company. And even if it's super modest, even if it's like dead simple, like Confluence wrapper that we can use in Slack, I think that would be satisfactory. But my hope is that it expands to something much, much more that has the ability to stitch together essentially all of our internal systems and enable us to do systematic research in all knowledge worker contexts in the company. All right, so that's pretty much it. Maybe we... Oh, sorry, last thing before I turn it over to questions. I want to talk about retrospective thinking. So this is like, I guess I've already talked about it. It's just to give it a name. It's this notion that after some agent run happens, and you've returned the answer and the user is sort of satisfied, you can do a separate sort of out-of-band processing, which is, let's look back on this whole thread and let's see if we can update the knowledge base with insights that were discerned as a result of a bunch of these like tool calls. That's it. So I'm calling this retrospective thinking. And so net, like these are, I think, some of the building blocks or principles. We have evals, we have dspy, we have writing back to knowledge systems, obviously implying that we can read from these knowledge systems as well. And then we have retro, so look back retrospectively on real agent runs, and then encode insights back into the knowledge system. I think these ideas are super interesting. I think we should apply them. And I'd love to collaborate with people at the company to see how we can do this. And so with that, thank you. I'll pass it over to you. Let's do some questions. Go ahead, Benjamin.
Yeah, thanks for the talk. Super interesting. One thing that I struggle with a little bit, and I would love to hear your opinion on it, is that like with this kind of evaluation framework, it's not exactly one-to-one with the software 2.0, and I like the way that you did that comparison, because you're changing not the weights in this case, because there are weights, you're changing the inputs, right? And that sort of gives me a little bit of like an anxiety, I guess, because the assumption is that the inputs, when we read them, mean something to us, but that may not mean the same thing internally to the model. And so I'm wondering if you have any thoughts about that, or if you encountered that.
Yeah. So it's tempting for us to really anthropomorphize these models because they make them like, I don't know, more relatable. Anthropomorphize means like, think of them as human-ish, right? And I think most people generally do that, but they're not human like at all. And they have these quirks, they have these strengths, they have these limitations. And the whole sort of arcane art of prompt engineering or context engineering is just this question of how do I get better at providing instructions to a model to get it to perform how I want it to. So my sort of philosophical stance on this is, I don't really care what's in the prompt itself. I just care that it performs. And in the same way that I don't care what the specific neural network weights are. And here an example is actually, you guys have seen these like thinking models, right? So the thinking model, basically, you give it a question, and before it produces some answer, it's able to just sort of have some internal monologue of thoughts that enable it to be more effective at answering a final question, right? And as you use a thinking model like GPT-5, or literally all of them are thinking nowadays, you kind of get a high-level overview of like what it's actually thinking about. But behind the scenes, the actual tokens that are going into the token stream when that model is running are fully opaque to us. Like we don't have access as consumers to the actual underlying thought stream. And the very, very interesting part, there's an interesting tweet by Andrej Karpathy from last year where he said, you'll know that your reinforcement learning system is working if the thought stream tokens are just complete gibberish. Meaning what's happening is that thought stream tokens are representing some abstract thing in the model's quote unquote mind in this like crazy embedding space. But because those tokens, the thought stream tokens, we are not training on them, meaning we're not rewarding the model for having those tokens be useful in the eyes of an English like reader. Instead, we're just rewarding the model based on how well it performs on the task at hand, which is producing the right answer. It basically means that the thinking thought stream tokens, if done well, it just ends up becoming like gibberish, uninterpretable to us as humans. And so I think you can extend this idea. And the extension of the idea is that we should be agnostic to the prompts completely. Obviously, maybe they're useful in having some starting point as like a straw man prompt, but we should really double down on this like eval structure and then just let the sort of prompts emerge as they might emerge. I'm not sure if that answers your question, Benjamin. Brian, go ahead.
Yeah, thanks for the talk. This is definitely a very exciting topic that I've been also been paying a lot of attention to, and especially thinking about it in the context of like areas where we're using prompts today. I think especially what you're showing here with being able to do evals and such is really important. I was just having an open-ended thought about like how do we actually get the training data and like the desired output data that helps us to get the outcomes that we want. I guess because the way I've seen ML in general is that data has always been like one of the biggest issues, right? Like getting good data. So how do we do that at scale to get like the right data, depending on which problems we're trying to solve?
So I think the first question to ask is how much data do we actually need? Meaning, what's the balance between data quantity and model quality? And clearly, it's like some sort of asymptotic relationship, meaning if you have very, very little data, the model performance is bad. But if you have tons of data versus tons and tons and tons of data, maybe you're only getting like incremental improvement. So what does that curve look like? And it turns out for these kinds of systems in dspy, on the order of dozens, literally dozens, so less than 100 examples, is sufficient for you to be able to explore some prompt space in order to be effective. And some systems go so far as to getting hundreds or thousands of examples, but I don't think I've seen examples in the tens of thousands. And so really, you're talking about dozens to get some product that is effective. And once you have that, you can call that bootstrapping, so to speak. You then have real users, and then you simply look at the real user interaction data to see the real queries. And then maybe you even like manually talk to the underlying people that are asking the question and say, hey, like, what would you have expected? And then maybe you go talk to some like internal expert who knows the real answer to the question. Then you say, what would the right answer be? And you use that, you maybe spend a couple hours worth of time to get one really good golden training data sample. I think you can probably do this and end up with, I don't know, dozens of examples without too much manual effort. And the beauty of this is that you can be sure that the quality of the examples will be really high because you spent a lot of time on it. And then I think if you pair that with having a really high quality eval, my feeling is that you could do this relatively straightforwardly. It isn't the same as like the way people talk about training LLMs and needing like tons and tons of mountains of data. It's very dissimilar to that because we're not actually training a model. We don't have to get like the LLM, like neural network weights. Like the process of gradient descent and backpropagation and training weights for multi-100 billion parameter models necessarily requires tons and tons of data. But I think the process of this generating plausible prompts, English prompts, based on a bunch of samples only actually requires dozens of examples. So it's like a totally different game that we're playing. And that's great because you could just literally brute force it. And it seems not too crazy to just spend a few hours with a group of people and collect this nice golden set. Go ahead, Andrew.
Good morning. Yeah, I like this structure of an eval framework. I've been working with this a little bit recently. I've been running into issues where with the same inputs, it produces wildly different results when evaluating, especially when it comes to like laziness and context size. It seems like sometimes it's 100% matches, sometimes it's like 30%. Just curious what your experience has been like.
Yeah, so this I kind of hand wave my way around it while suggesting that it's important, but the ability for you to produce an eval that's actually really good is pretty complex. It's harder, I would say, than a neural network eval, which might be like given some probability distribution and a desired probability distribution, it's actually like very easy, statistically speaking, to come up with a single number about the distribution similarity. Whereas if I have some text and some other text, like how do you actually quantify whether these two things are similar? And so there's a few approaches. I think the first thing is there's some like baseline criteria that's like binary that you probably want to encode as simple rules. So for example, does it have the right format? Like in this Confluence thing, I really wanted to output like a Slack flavored markdown. So I could pipe that output right into like a Slack thread. And I want it to have all of the references at the bottom, and I want the page titles for all the references to be the actual Confluence pages. So some like basic rules that I think you can simply quantify as like binary, did you do it or not? And then beyond that, for the sort of semantic similarity, there's a lot of ways you can go about doing this, but the sort of simplest, I guess, way would be this thing called semantic F1. So an F1 score is like a sort of software 2.0, I guess, or statistical way you can compare two things to produce some eval. Semantic F1 is like the application of that, but in blocks of texts. So given two pieces of text, like what is the sort of semantic overlap of ideas or tokens across these two blocks of text? That's like one way to do it. It's not perfect, but you can get more advanced. Maybe sort of shifting a little bit, you talked about like the non-determinism of the LLM system itself. So given some user input, if I call it multiple times, it produces different output. Like this is like definitely a known problem. I think it's quote unquote solvable in a few ways. Like I think some LLM providers like OpenAI allow you to provide some random seed so as to make the process deterministic. But I've seen some reviews where people haven't actually seen the actual determinism that you would expect. But at the very least, providing it seems like a first step to reduce the sort of stochastic nature here. I think another thought is simply by collecting more data and having more training examples, you sort of average out the idiosyncrasies of like randomness, I guess. Meaning maybe in some calls, like you'll sort of randomly converge towards like a positive solution, and in other calls you'll randomly converge to like a poor outcome. But that hopefully that randomness sort of averages out as your sort of sample size of training data increases. That I think is another way of thinking about it. And maybe the final thought would be like, nobody actually really knows. Like everything that I've said is all just like one big hypothesis. I think really what this is begging is for us to just try it. And I don't think the barrier to entry is actually really high whatsoever. And I think in the process of trying it, you'll actually learn like how to go about like solving like the specific problems you run into. So yeah, hopefully that's maybe a few responses here between semantic F1, providing the actual random seed to the API providers to increase determinism, stuff like that. I think are maybe some things that you can do. But again, it's uncharted territory, so nobody really knows.
Yeah, Dwight, I had a question.
Sure.
Thanks for giving the talk. And so for the use case of like searching Confluence, do you think this sort of approach would work where it prioritizes like the latest information? Like this model, it's able to come up with heuristics on its own, like sort by like the latest document, because I can imagine there's a lot of conflicting documentation in Confluence. So
Mhm.
how does it choose like which document to pick as the source of truth?
Yeah, great question. So I think there's a couple of ways you can think about this. The first way would be we have some human intuition around what the likely good solution is going to look like. So let's just encode that. Let's start by encoding it in the form of this specific, where did it go? dspy. This signature in the actual instructions, right? Because these are actually just initial bootstrapping instructions. These, once you start off with this, like they get transformed into like this stuff, right? And so you could start off by encoding your sort of prior knowledge, so to speak, about what a good system might be. Let's say it looks at dates, and then if stuff hasn't been edited in the last 2 years, it's much more skeptical about the quality of that information. Or I think the more interesting alternative approach is you just get a bunch of training data. And ideally, the training data results in agent runs where some runs perform searches that converge effectively, while other runs perform searches that look at old pages and result in bad outcomes. And simply through that semi-random process, the dspy optimizer will automatically determine the importance of the date field in the context of the specific questions that you've provided it. I think that this is actually the more reliable way to go, in the sense that we have just articulated a single example of the date field being plausibly useful in answering queries, but it might turn out that there's dozens of other heuristics, hundreds, thousands, whatever, right? That simply wouldn't even occur to us as humans. And so by taking the approach of evals, you're agnostic to which heuristics the model actually determines are useful. And hopefully that translates to heuristics that you wouldn't have considered at all, which further translates to model effectiveness that was out of reach to you before. And there's examples of this. So if you look at the actual dspy paper, they show clear examples in specific domains. I think there was like a medical domain where the dspy agent, its performance on some sort of medical task, I don't know the exact specifics, was something like 25 percentage points higher than the performance of the next best system, which was handwritten, hand-tuned, meaning that the prompts themselves were authored by humans, right? So simply through this like automated process, the optimizer was able to discern the relevant heuristics and perform 25 percentage points better than the human experts. So I think we saw this in software 2.0, where the models got so good at their tasks, they quickly reached like superhuman ability, whether it's chess, whether it's image classification, whether it's fraud detection. I think we're obviously going to see a similar thing in LLM-based systems as well. And ultimately, it's a matter of articulating what better means in the form of this eval. Go ahead, Nick.
Yeah, but thanks for the talk.
Yeah.
I'm curious. So I haven't really explored this stuff too much, but like I've read about the concept of fine-tuning LLM models, or like training LLM models on your own data sets. And to me, it seems like there's some inherent overlap between what you're talking about and that sort of theoretical stuff that I've read about. So I was wondering if you could share some thoughts on that. This seems like a prompt forward approach to getting the same kind of output, but what does the other approach look like?
Yeah, great question. So it turns out that fine-tuning LLMs and prompt optimization are not actually mutually exclusive to each other. They're complementary. And it also turns out that dspy comes with a mechanism to fine-tune models. as a part of the optimization process alongside the prompt optimization, which is pretty cool. You just get both. And so the benefit is that you end up with a bespoke model, and in it being bespokely trained on your data set, it's able to sort of forget about concepts or ideas that are irrelevant to the specific domain of whatever it is you're trying to use it for. And more of the weights are able to be used for the specific task at hand. I guess that's one hand-wavy way of thinking about it. So people are doing this. I think there's some major downsides of fine-tuning, though. You can't really fine-tune like a bleeding edge model, right? We don't have access to GPT-5 or Gemini 2.5's weights. But I think more importantly is the economics of what it takes to actually run these models, in that they're so large that the sheer volume of GPUs required to be able to run inference is like insane, right? So if you had a bespoke model that's not being used 100% of the time, meaning it requires, let's say, I don't know, dozens of A100 or H100 chips in order to actually run inference at scale, or not even at scale, like at all, right? Within some reasonable latency, it requires a certain level of scale for you to actually saturate the throughput of all of these GPUs, right? So if you're operating at a lower scale, you're simply not saturating the GPU throughput, and therefore the cost of the GPUs on a per query basis basically skyrockets. What I'm saying is, like, the only economically feasible way to fine-tune large models is to guarantee almost that you have near 100% utilization of the hardware. Otherwise, it's just gonna be way too like prohibitively expensive. And that is almost like nothing compared to the actual technical complexity, honestly, of doing this training, especially when it comes to these large models. So I think what I would kind of conclude with is it's actually trivially easy to iterate on prompts. It's like comparatively 100 times harder to fine-tune things at a technical level. But even when you have fine-tuned a model, it's also 100 times harder to run it, as well as, like, economically speaking, do it sustainably. So with maybe like a couple years ago, when everyone was talking about how GPT 3.5 was a product of fine-tuning, I think there was a lot more excitement about the opportunity to apply fine-tuning in all domains. But I think as people actually started to do it, they started to realize that we have other levers in the form of prompt optimization here that are 100 times easier. So let's pull on them. And I think what they discovered, like the dspy people, they showed that if you, like, for a specific domain, with obviously a bunch of training data, they did just fine-tuning of like a open weights model, and they did like just prompt optimization. And I'm pretty sure they showed like the prompt optimization on the vanilla model was more performant than the fine-tuning of that same model, which to me was really surprising. Like, it means like you can just provide the English instructions to get the models to do what you want to do, instead of necessarily having to update the weights. Again, not to say that these are mutually exclusive, because technically you can apply both. But the difficulty level, I think, is a major factor. So yeah, hopefully that makes sense. Cool. All right, we're at the hour mark over here. Thanks, guys. It was super fun. In terms of next steps, I'll probably just be using the cursor channel to talk more about these ideas. And I've got some like straw man code here for a Confluence bot. I might make some progress on that and release it both as like a MCP server, which you can plug into via cursor or whatever you use, as well as a Slack bot, so that anyone without MCP client can actually use it. I'm like almost there. So as soon as I get that, I'd love to sort of notify the channel and anyone who's interested in collaborating. I'd be happy to add you on code reviews and meet together or co-write design docs, whatever it is that you're interested in. I'm very eager to collaborate with y'all. So yeah, thanks for joining, and I'll see you guys around.
Thanks again, Evi.
Thank you.
Thanks, Edward.